So, all right, so last time we got to indeterminate form, and we said when you have 0 over 0, there are two things you can do to get around it. One is factoring and one is rationalizing, which we did. So let's move on to limits at infinity. So do you remember in the last lesson we said you can find a limit essentially as x approaches a finite number. X approaches 5, x approaches -3. And you could get either a number or infinity. And then you also find the limit as x approaches infinity. Remember, like that was a different thing, right? So how do you do that algebraically? Okay. Now, I've talked about this all the time. So take a look at this first function here, which is an even function, right? Even function, both ends go up or both ends will go down. That's an even function. And here we have an odd function. So you see that if you look at x as x approaches infinity, in the case of the even function, you're going to get infinity for both or negative infinity for both, right? Whereas for the odd function, limit as x approaches positive infinity will be positive infinity. Limit as x approaches negative infinity will be negative infinity, or vice versa if it's a negatively odd function, right? So here it's right here is some summary of that. We know this already. Now, polynomials, right? Polynomials, the limit of a polynomial function at infinity. Basically, I know I've talked about this before. At infinity, as x approaches infinity, think about if you have a polynomial function, like for example, p of x is 3x to the 7 plus 5x to the 4 minus 2x cubed plus x, right? Okay, if x is infinity, or not even infinity, suppose x is 1,000,000. Then here you have 1,000,000 cubed, and then here you have 1,000,000 to the power of 7. When you have 1,000,000 to the power of 7, anything else will pale in comparison. So you could essentially ignore it completely. So when you're thinking about x approaching infinity, the only term that really matters is the term with the highest degree, because everything else just pales in comparison. So I can throw everything away, and now what I have is a positive odd function. So I know that at positive infinity, this is going to go up. At negative infinity, it's going to go down. I don't care about all that. Now, at x approaches 0, the others make a huge impact. All right? But as x approaches infinity, everything other than that leading term is, we say, negligible. Yeah.
So let's just say x was 1,000,000 and it was 3x to the 5 minus 3x to the 4.
Still, because 1,000,000 to the power of 5 is 5 times 5 zeros, right? 5 times 6 zeros, that's 30. And then 1,000,000 to the power of 4, that's 1,000,000 times less. You see that?
Yeah.
That only has, it's like 24 zeros versus 30.
You say it with like 30 million or like however many.
Right, I mean, it's like, it's 1,000,000 times less, right? X to the 4 and x to the 5, it's 1,000,000 times less. So it pales in comparison. Okay, so here we go. Let's evaluate each limit. Again, I only take the term with the highest power, not the first term, because, you know, it could be out of order. The term with the highest power, so the limit as x approaches infinity, I don't need to write it, it would be what? Positive infinity, right? And with these, students always ask me, do I need to show work? The fact of the matter is, I would like you to be at the point where you look at it and you know, okay? If you want to show some work for, you know, by chance to get some credit, you may or may not get credit. I don't know, that's up to you, but I'm not looking for any work, right? Here, it's this one, and as x approaches negative infinity, where is it going to go? Positive infinity. right? So if you think about it, it's negative x cubed. So like at negative 10, you know it's going to be positive, and then it's just going to keep going further and further up, right? Also, y equals x cubed looks like this. Y equals negative x cubed looks like this. So as x approaches negative infinity, that goes to positive infinity. Okay? All right, here, which one do we take? The 4x to the 5. So as x approaches negative infinity, there is a plus in front of that. It'll be negative infinity, right? Because it's 4x to the 5th, it's like this one. And as we go to negative infinity, yeah. So it'll be negative infinity. You're right, whether the exponent is odd or even. Mm-hmm. And then here, negative x squared. So this is a parabola, but it's negative, so it's facing down. So no matter which way you go, they're going to go to negative infinity. All right. So these were polynomials. Well, what about reciprocal functions? We know by now that this is what a reciprocal function looks like, right? And we've done this a million times. When f of x is 1 over x, can x ever be 0? No. Can y ever be 0? No, right? But as x gets infinitely large, what value does x approach? 0. It approaches 0, but it never actually equals 0. And you see that 1 over x looks like this. It's positive in the first quadrant. When x is positive, so is y. Negative, they're looking at positive and negative infinity. So as x approaches infinity, the limit is 0. And as x approaches negative infinity, the limit is 0. Okay. And you can tell that the negative 1 over x will look like that, will look the same. Well, it won't look the same, but the limit will be the same. Right? This is negative 1 over x. When x is positive, y is negative. Again, as x approaches infinity, you approach 0 for that as well. Correct. Right. So let's do a little bit of a summary. Limits of rational functions at positive or negative infinity. Rational meaning fractions, right? Okay. No, rational just means, when you have like a polynomial over a polynomial, like x cubed over 3 minus x. Okay, here's what we do. Compare the degree of the numerator and the denominator. The highest, right? The highest exponent in the numerator and the denominator. Now, if the degree of the numerator is less than the degree of the denominator, numerator is less, denominator is more, the limit is 0. Okay? Let's just okay, listen. I don't like you memorizing things. So let's not memorize. Let's reason it out. Let's look at an example. Numerator has a lower degree than denominator, like this example here, x squared, x cubed. Okay? So everything else other than the x squared and the x cubed is negligible. So this is the limit as x approaches infinity of x squared over x cubed, right? Which is the limit as x approaches infinity of 1 over x. And what would the limit of that be? As x gets infinitely large? 0. Now, do you have to show me all this work? No. You can if you want to, for a chance that you might get partial credit. You might get partial credit, that's the key word, but you don't have to. I just want you to know, more x's on the bottom, as x approaches infinity, that's just going to be 0. Okay. If the numerator has the same degree as the denominator, then the variables will cancel, and the limit is just the ratio of the leading coefficient, right? Like, for example, this one. This is the limit as x approaches negative infinity of negative 2x cubed over 6x cubed. The x cubes cancel, so it's just negative 1/3. Okay? It's just like asymptotes. Oh my gosh. We're actually going to do a whole section of us. Oh my gosh, you guys are doing my job for me. There we go. This is it, right? I never say it until you guys figure it out, and then we all know. Okay? But this is leading up to asymptotes, because the asymptote, horizontal asymptote, is just the limit as x approaches infinity of the function. Isn't that cool? Right, depending on the function. Right.
Wow.
Say that again? Oh my gosh, you guys are so getting this. Okay, I'm so happy. Huh? What? There is a screencast going. The degree of the numerator, okay, if the degree of the numerator is greater than the degree of the denominator, then we have more x's on top. So when you cancel, you're going to have more x's on top. And if x is approaching infinity, then the whole thing will approach infinity, right? Or dne. So here's what we have to do here. I'll tell you. So the limit, this is going to be the limit as x approaches infinity of these two. So it's going to be x to the 5 over negative x cubed, which is the limit as x approaches infinity of negative x squared. And that's going to be what? It's a parabola facing down, okay? So it's going to face down, so negative infinity. Because it was x to the 5 over negative x cubed here, right? You take the entire term and the entire term. Okay, so let's evaluate these then. The first case, it'll be what? More x's on the bottom, so 0. The second case, this is the limit as x approaches infinity of negative 3 over 5x. So it'll be how much as x approaches infinity? Negative infinity. Right? Negative 3 over 5x, that's a line. And you know that at negative infinity, it's going to negative infinity. Here, boom, boom, same, 7 over 2. Okay? All right. Okay, piecewise functions. This was actually what we're supposed to start with today. Piecewise functions. To evaluate limits of piecewise functions, okay? And obviously, if this is at the partition, right? If limit as x approaches to the value of the partition. Evaluate the left hand and the right hand limits at each partition. And the limit will exist if the limit as x equals c plus is the same as the limit as x equals c minus. So if it's the same limit from the left and the right. And we have done a little bit of this. So here, for each limit at x equals c, find the limit and evaluate the function at x equals c. So first, the limit as x approaches 3 of this, I'm going to call it f of x, okay? So here's what we do. Evaluate this top at 3, right? So here's what I'm going to do. The limit at 3 minus of f of x is what? 2 times 3 plus 7, that's how much? 13, right? And then the limit as x approaches 3 plus of f of x is how much? 3 squared, that's 9 minus 1, 8. So what does that mean? The limit, right. Okay. All right, so let's do the next one. The limit as x approaches -1 from the negative side of f of x. They're different, yes. Is how much? -1, so I have 1 plus 2 is 3. The limit as x approaches -1 from the positive side of f of x is -3 plus 6, that's equal to 3. So the limit at -1 of f of x is 3. The width in millimeters of an animal's pupil is given by that formula, okay? Because you know, right, if you're in a dark room, your pupils will dilate, and if you have light coming in, then they will, okay. X, this is important, so X is the illuminance of the light shining in the pupil, measured in measures, LUX, that's the unit of measure. Write a limit to describe the width of the animal's pupil when the light is at its maximum. When the light is at its minimum. The light we said was X, right? When the light is at the minimum, that means this is the limit as X approaches 0. Okay? No. Because it's X is like how much light there is, and you can't have negative light, right? Then find the limit and interpret your results. Okay, so let's do that. So we're going to do d of x, the limit as x approaches 0 of d of x, which is equal to the limit as x approaches 0 of that complicated looking function over 4x to the negative 0.45 plus 10 equals 2. All right, we have negative exponents, right? Well, why don't we write those as fractions? So 152 over x to the 0.45 plus 85. And then 4 over x to the 0.45 plus 10. Now, can I possibly get rid of those? I can get rid of them. Right. So, this is going to be 152 plus 85 x to the 0.45 all over x to the 0.45. And then same thing here, 4 plus 10 x to the 0.45 all over x to the 0.45. Okay, so those go away, the denominators. So now what I have is the limit as x approaches 0 of 152 plus 85 x to the 0.45, 4 plus 10 x to the 0.45. Now, when I plug 0 in here into the x's, right, what do I get? 152 over 4, which is about 38 millimeters. Okay. Now it says interpret your results. So you have to be able to write this, what this means, the significance of this in English, in a coherent English sentence, right? Now, what is this? When the light is at its minimum, okay, the animal's pupils have a dilation of 38 millimeters, okay? So, yeah. Mm-hmm.
That one, and you just 152 over 4. We have the same answer.
No. No, because that was for polynomials. That applies for polynomials. And I know that in this case we might get the same answer, but that applies for polynomial functions. And polynomial functions are defined as functions who have exponents of integer value, positive integer values. Okay. Now, write the limit to describe the width of the animal's pupils when the light is at its maximum. So this is as x approaches infinity, right? So let's do that. This is the limit as x approaches infinity of 152. Okay, so take a look at what I'm going to do. I already simplified this once, right? So I don't want to do it again, and I'm just going to start from here, right? So I'm going to say 152 plus 85x to the 0.45. And here we can take this, right? We couldn't before because it was a negative. But here we can take this. So this is 85x to the 0.45, 10x to the 0.45, and that's equal to 8.5 millimeters. Okay. Right. So as x, as the light approaches max, yeah, or approaches maximum illuminescence, the pupils have a dilation, have a width, I guess, of 8.5 millimeters. So you see how it gets smaller? Okay, here's some chemistry for you guys. Yeah, here's some chemistry. In molecular theory, the root mean square speed measures the average speed of particles in a gas, right? You know the gas laws, right? Those of you who've taken chemistry, you know gas laws, and PV equals nRT, and right, as temperature increases, the velocity increases, and so on and so forth. So this formula, VRMS, root mean square, it describes the average speed of the particles. Okay, I love that stuff. Oh my gosh, this is like an area which is called physical chemistry. So it's like the physics of the chemistry, and it's so cool. Okay. And R, everybody knows, is the gas constant. T is temperature. M is the molar mass of the gas particles in kilograms per mole. Okay. Find the limit as M approaches 0 of V. So the limit as M approaches 0 of V is equal to the limit as M approaches 0 of 3RT over capital M. And what happens? If M is 0, well, it'll be what? This, okay, so,
is it a reciprocal?
it's okay, R is a constant, 3 is a constant. T is pretty much going to be a constant because you're doing it at a constant temperature, right? So, all these is a constant. So pretty much what you have is a constant over a variable, which is like, 1 over x. It's a reciprocal function. Right? It doesn't matter. Because, okay, so forget about the square root. A reciprocal function approaches what as x approaches 0? Infinity, right? As x approaches 0, 1 over x approaches infinity. right? Okay? So take a look at our functions here. As x approaches 0, it approaches infinity. Okay? We're talking about velocity, so we're going to keep it positive because we're approaching it from the positive side, right? The mass is approaching 0 from the positive side, so it's going to go to positive infinity. The square root of infinity is, guess what? Still infinity. Here it is. Okay, so basically this is just going to be infinity. And then we'll talk about, interpret your answer as the mass of the particles approaches 0, velocity becomes infinitely large. Okay. And then I'm going to tell you a couple of things, but I'll tell you later. Okay, so now how about as m approaches infinity? So this is going to be the limit as m approaches infinity of 3RT over m. And as m approaches infinity, what is all this going to turn into? 0. Does that make sense? Does that make sense that as the particles get super light, they're going to start moving very quickly? And if the particles get infinitely heavy, their velocity is going to be 0. It makes, it's going to be approaching 0. They're still going to be moving, but very slowly. It makes perfect sense, right? So as the mass of particles gets infinitely large, their average velocity approaches 0. Okay, now in example number 9 and in example number 8, did I use the word it? Did I use the words go up or go down? No. These are generic terms that you never want to use in math. My pet peeve in math, and when I teach calculus, when I used to teach AP calculus, my pet peeve was it goes up. Oh my gosh, I wanted to pull out my hair. It goes up is not mathematically sound. The velocity increases, the function increases, the value of f decreases, okay? Never it, because you don't know who those pronouns belong to. Okay, remember sequences and series? And remember, if we had to figure out if things diverged and converged, let's do it using limits. Because how did we figure out if things were divergent or convergent? Well, we tried n equals 1, n equals 2, n equals 3, and then we extrapolated that as n approaches, infinity, da-da-da-da-da. Oh my gosh, isn't that a limit? That is so a limit. So yes. Isn't that cool? So limits, right? You can write limit sequences as a function, and then the limit of the sequence is the limit of the function. So you can see here, these are like the explicit formulas for an. Remember explicit formulas? Right? So here we would generate, let's say, a2, the second term, and it would be 4 over 2 squared plus 1, right? And then so we did a1, a2, a3, a4, and then we said, they look like it's decreasing to 0, so it's going to converge, whatever. So now, if the limit exists, then the sequence converges. If the limit does not exist, then the sequence diverges, right? Okay, because if the limit exists and goes to a certain value, then we're good. But if it goes up indefinitely to infinity, then we have no clue. Okay, so here it says, write the first 5 terms. I'm going to skip that because I know we've done that. I'm just going to go to the finding the limit, okay? So we're going to do the limit as n approaches infinity of an. This is the limit as n approaches infinity of 4 over n squared plus 1. What do you guys think? 0, infinity, or another constant? 0. I say 0 because you have more x's on the bottom, more n's on the bottom, and as those n's get infinitely large, you're going to get something over infinitely large numbers, which is 0. Okay, here, the limit as n approaches infinity of Bn is, okay, what we're going to do here, this is a rational function. We're going to take the highest degree on top, highest degree on the bottom. To do that, you have, I'm going fast because I'm on a time crunch here. To do that, and I'm also excited. We're going to multiply, right? So technically you would have to multiply everything out and get the leading term. But if all we care about is the leading term, then I can do that by getting the product of just these. Okay? So 9 times n times 2n over n cubed times 6. Okay? So this is the, oh, I made a mistake. What did I leave out? I should have limit in there. -1. This is the limit as n approaches infinity of 18n cubed over 6n cubed. This is 3, so it converges. And this converges, and everybody converges, and this is fantastic. So, for homework, for next time, you're going to finish the 3 here and do these. And as you can see, they're super quick. Okay?